All right, so here's the chemical reaction we showed at the very beginning of this chapter, right? It's called the thermite reaction. It's used to weld railroad ties together because it releases so much heat. It gets the iron so hot it can melt iron, make it liquid, and the liquid iron can flow between two railroad ties, right, which are the tracks of railroad, and weld them together. Okay, so the question here is, what mass of iron is made if only 500 kilojoules of energy are released?
Equal sign.
Okay, very good. Equal sign. What goes to the right of the equal sign?
Mass of iron.
All right. And what goes to the top left here?
We want kilojoules.
Wait, hold on just a second. Why don't you let everybody else at home give it a shot, and then they'll come back and see how they're doing.
Okay.
All right. Hopefully you went home and took it a shot, or went back and tried it. What are you going to put at the top left here, Fred?
500 kilojoules.
Very good. 500 kilojoules, because that's how much energy they provided us, right? And then what are we going to do?
We know that 848 kilojoules are released for every 2 moles of iron.
Okay, very good. 848 kilojoules are released for every 2 moles of iron. Where'd you get that?
The equation.
That's right. This equation is related directly to this 848. So 2 moles of iron are produced when 848 are released. Okay? So we didn't release 848, so we're going to get less than 2 moles of iron, but we don't want moles of iron, right? All right, what do we want?
Moles or grams of iron.
Very good. So we're going to go from moles of iron to grams of iron, and we'll be there. Molar mass of iron?
55.847, it says.
Very good. Okay, so 500 times 2 divided by 848 times 55.847 should be 65.9 grams. Excellent. Now, we've been drawing these diagrams every once in a while, a little bit, and we call them energy diagrams, but we can call them enthalpy diagrams. I mean, it just depends whatever you want to have on your y-axis. So if we're just looking at our enthalpy, right? So if enthalpy is what we're looking at, H for the chemical reaction, then we call them an enthalpy diagram. And what we want to see for an enthalpy diagram like this is that if you have a chemical reaction, in this case the chemical reaction that's kind of being explored is carbon combining with oxygen to form carbon dioxide. And we said that the energy of the carbon dioxide was what, higher or lower?
I think you said that it was lower, but I can see from the diagram there that it's lower.
Okay, yeah, you can see right up here on the diagram. Carbon dioxide's energy is lower than that of carbon and oxygen. Again, this is the heat energy. Okay, and the 393.5 is the energy that's released as the carbon and oxygen are reacted to form the carbon dioxide. Well, if the carbon and oxygen only partially react and form not carbon dioxide but carbon monoxide, then the amount of heat energy that's released is less. And then if that carbon monoxide and oxygen continue to react to form the carbon dioxide, you end up with the same amount of energy in your system, carbon dioxide here, that you started with. All right? So the reaction, if it proceeds in one step, releases all this energy. But if it proceeds in a half step and then half again, it will release the same amount of energy, but in small portions, smaller portions, right? In aliquots that add up to the total. This recognizing that this occurs is called Hess's law, after scientists who kind of explored this. But the point is that essentially we're saying if I have this reaction, carbon and oxygen forming carbon dioxide, and let's say the delta H here is a negative 393.5, What this is saying is that carbon dioxide, if it were to decompose to carbon and oxygen gas, the delta H would have to be what?
Positive 393?
That's right, a positive 393.5. Because we have here the same material that we ended with, and we're going to back to the reactants. All right? And we're also basically saying that if you, every small step along the way, maybe there's other chemical reactions that are occurring, kind of partial chemical reactions that are occurring along the way, whatever the ending products are, minus the reactants, that's what's going to tell you how much energy was released. Okay, so here's an example. If I have this chemical reaction where iron combines with oxygen to form iron oxide, and I know how much energy this process, in this case, releases. And then I have another chemical reaction where I have some iron oxide combining with aluminum to form aluminum oxide and iron. And I know how much energy this process releases, right? Well, if I add these two reactions together, and when you say add two reactions together, what that basically means is you write all the reactants from both reactions on one side and all the products from both reactions on the other. So, for example, if I'm adding these first two reactions together, I'm going to put all the reactants. That's 2 atoms of iron from the top there, 3/2 atoms of oxygen, and then also Fe2O3 and 2 aluminums, right? So I wrote the reactants for both of these reactions right here. And then if I can write the products for both of the reactions, Fe2O3 and Al2O3 and the 2 irons, right? So now I wrote all the products for the reaction over here. The energy for this reaction here, the energy for this reaction has to be the same as the sum of the energy of these two reactions. Now in this reaction here, we have some spectators, some things that aren't performing any chemistry. See how the irons aren't doing anything? All right, and the iron oxide is also not doing anything. And so that's where we got this third chemical reaction. We crossed out the spectators, and what we're left with is our oxygen combining with aluminum to form aluminum oxide. Now, we wanted the appropriate amount of oxygen to combine with aluminum to form a single mole of aluminum oxide in this chemical reaction. And so we used a fraction of the balanced equation, right? To have this equation completely balanced, you'd have to multiply all these by 2, and then that'd be 6, 3, and 2, right? Okay. No, sorry, 4, 3, and 2. Okay, so Hess's law basically says that if you take two reactions and their delta H's and add them together, the resulting reaction's delta H will be the sum of those two delta H's. Okay. Also, like we noted, if you reverse a chemical reaction, it will change the delta H, the sign on the delta H. Another thing that we could think about is if I took 2 carbon dioxides and produced 2 carbons and 2 molecules of oxygen gas, the delta H for this would be not the 393.5, but it would be 2 times the 393.5, which makes sense because we just said that if you take this and add it to another one of these, it would be that times 2, right? So putting 2 in front is kind of the same as adding it to itself. All right. So what that allows us to do is we can calculate delta H's for unknown reactions if we know delta H's for known reactions. So here's a chemical reaction. 2 hydrogen gas combining with nitrogen to form N2H4. And we're going to use, and we want to know the delta H for that chemical reaction. We want to know how much heat energy is either required or released. And we can use the heat energy in this information here to find out how much energy this reaction will either require or release. And what we do is we look at this chemical reaction here and think about how can we add these two together in such a way that we result in this chemical reaction. You see anything?
Those two chemical reactions on the bottom, we need to add them together to get the top one?
Yeah.
Well, you can't do that because the N2H4 is on the wrong side.
Okay, good. So you've noticed that the N2H4 that we need to have needs to be on the product side, right?
Yeah.
So what we're going to do is we're going to first reverse that first reaction, right? If we reverse the first reaction and then just change the sign, now we have another chemical reaction here available to us that we can use to maybe add to the second one here and get that answer.
Let's see, would that work? The second reaction plus that new one, you'd end up with a nitrogen, and you'd end up with two hydrogens on the left, and you'd end up with N2H4 on the right, and you would have no ammonia. Yeah, so that's it.
Very good. So then we can add the second reaction, and the result of that is this. And then we cross out anything that's not doing any chemistry, and we see that we get this. Well, this one is not quite done there. We've got to cancel out one more. And we get two H2s plus the N2 forming this. And so the resulting energy will be the delta H for this flipped one plus the delta H for this second one. Okay? Very good. Did you follow that?
Yeah, I got it.
Excellent job.